All right, let's go back to here. This one right here. How do we show this part? Because we're going to see this separation of variables a lot throughout the course. So let's go ahead and do it here. Okay? So let's prove this expression right here, that if this is the case, then we can write that and that. Okay? So those are conclusions. So we assume that big psi is equal to little psi times function of time. Okay? So let's apply that to let's plug that into our time-dependent Schrodinger equation. Okay, so this one, IH hat, H bar d psi dt equals H psi. Okay? So H bar, partial derivative of big psi dt is equal to H hat psi. So let's substitute. I'm going to say H bar derivative, partial derivative with respect to time. I'm going to write little psi times f, okay, equals H hat times operating on little psi times f. Okay. Now, I'm taking the derivative on this left-hand side with respect to time. Now, psi, little psi, does not depend on time, right? So as far as this derivative is concerned, this little psi is a constant. The variable here is time. So I can factor that out. I can move that out of my derivative. So this is going to be H bar little psi times partial derivative of f with respect to time equals. The Hamiltonian operator, we say, this is true, we say, if the Hamiltonian does not affect time, right? It's independent of time. So as far as this Hamiltonian is concerned in this particular case, f, this f right here, is independent of time, okay? So that's a constant. It only affects coordinates, right? Expressions that depend on the coordinates. So I can move out my f as a constant. So I'm going to say f times h hat psi. Little psi now, okay? You still with me? All right. Now, I'm going to separate my variables. I'm going to move everything that depends on time on one side and everything that depends only on coordinates on the other side. So I'm going to divide this by psi times f. I'm going to divide this by psi times f. Up. All right. So what happens? Psi cancels out on this side, right? And what happens on this other side? F cancels out. Now, the psi up here is not going to cancel the psi down there because that is not h times psi. That's h having, that's all, that's this h hat psi, that's an entire function, okay? That's a transformed psi, okay? So, what do I have now? H bar, partial derivative of f, okay, with respect to time over f is equal to h hat psi over psi. Okay. Now, if the equation is obeyed, we say, here's one side that depends only on time, right? It's an expression that might have time in it, right? And here's an expression that will have coordinates only, right? Only on Q. And this one's only on T. Q is coordinates. T is time. How can one side that depends only on time be equal to another side that depends only on coordinates? In other words, it doesn't matter what time it is. It doesn't matter what coordinates you have on the other side. Those two sides are always equal. How can functions of two different variables be equal? How can an expression that depends on one variable be equal to an expression that depends on another variable, then it must be that both expressions must be equal to a constant, right? So what we're saying is, whatever these expressions are, this left side must be equal to a constant, and that right side must be equal to the same constant. And we're going to call that constant E for reasons that will become obvious. So that constant is E. So we're going to say now that, so this left-hand side is IH bar df, and I'm going to take the partial derivative now since I only have one variable there. So IH bar over F df dt is equal to E. That's your left-hand side. And your right-hand side is H hat psi over psi is equal to E. And remember we said that these are the consequences of the Hamiltonian being not dependent on time, and if psi happens to be a function of coordinates times a function of time. But what is this one right here? How do you solve for that? df dt, let me rearrange that, is equal to F E times F over I H bar, okay? And I'm going to move the T onto the other side, so dF and F on the left side. So dF over F equals, and I'm going to move that I up on the top, so it's going to be negative I E over H bar, okay? So this is just negative IE over H bar, and then dt I'm going to move to the right. Okay, so I'm moving my F down here and my dt over there. Okay, what you have here is called a differential equation. You integrate both sides, you get the function. So if we integrate both sides, what's integral of df over f? ln of f. And IE over H bar is a constant. I can pull it out. Minus IE over H bar. What is the integral of T? dt is T. Right? Plus an integration constant. We'll combine the integration constant from both sides. We'll just have one integration constant. Okay? So can I simplify this? I can say this is log to the base E, right? So E to the negative I ET over H bar is equal to F. Okay? Take the inverse log of both sides times E to the C. Now E to the C is just another constant. We're just going to take that as 1. Okay? It's an arbitrary constant. Ultimately, the whole expression is going to have to be multiplied by a constant so that it's normalized. So we're just going to take that as, for simplicity, we'll just take that as 1. So our function of time is just e to the negative I et over h bar. Okay? And what's the other equation we have to solve? So we know the part that depends on time. So the only part that we really need to solve from here on is just this part right here. If we're only interested in stationary state, I can rearrange this to say h hat little psi equals e times little psi. This is the time-independent Schrodinger equation. Okay? The other one that you saw earlier, that's a time-dependent Schrodinger equation. Time-dependent, and then this one, h hat psi equals e psi. That is your time-independent Schrodinger equation. Okay?